In this video, we're going to be doing some simple harmonic motion practice problems. First, let's discuss what makes something simple harmonic motion. This is when you have a restoring force that is proportional to your displacement. So your F restoring is going to be proportional to negative x. This negative sign means that it is going to go back. That is the restoring component. Let's also talk about when the speed is the max. So you're going to have V max at equilibrium. And when is our acceleration going to be max? That is going to be at your maximum displacement. Also, what do we have that is going to determine our period? Our period is when our cycle starts again. We have cyclic motion when we have a restoring force and springs. So we have Fs is equal to negative kx. We're going to have our mass and our stiffness, which is k, from our spring. And if you're given a pendulum, it's going to be determined by the length, L, that you're given of the string, and also gravity, your gravitational constant, which is going to be 9.8 meters per second squared, not the amplitude. Let's quickly talk about the energy flow. At your displacement max, kinetic energy is equal to 0. Potential energy is max. Again, at your equilibrium, kinetic energy is going to be max. Potential energy is equal to 0. As we can see here, potential energy is greater when you're farther away from equilibrium because you have the potential energy to be stretched back or compress more. So from here, our energy constantly swaps from EQM to displacement, back and forth. Now let's solve some problems. Okay. So let's start here. A 0.65 kilogram particle in simple harmonic motion has an amplitude of 4.5 centimeters and a rotational velocity or angular velocity of 7.5 rad per second. So how can we do this? What you first need to know is your equation. We want to find the max velocity and the total energy. So we can start with the simple harmonic motion position equation. We have xt is equal to and using calculus, or you won't need to know this for AP Physics 1, but the derivative of v of t is going to be dx dt, and then that's going to give you v of t is equal to negative amplitude omega sine omega t plus angle. So in AP Physics 1, you know this from just looking at the graph, that when you have your cosine and sine, it's going to be shifted by a period. Or it's going to be shifted in its starting location. When you look at your graph. So yeah, when you have sine, it's like that. But when you have cosine, it's like that. Cosine x, and there's your sine x. So now what we have to do is we have to find the max value. We know that sine ranges from -1 to 1, and our maximum magnitude which we're going to use to find our velocity, sine omega t plus your angle, yeah, that's just going to be 1, as you can see here. The absolute value of that is going to be 1. So your V max is equal to your amplitude times your omega. You're just going to substitute in your values. You had 0.045 and 7.5 per second. Make sure that this is in kilograms because you want it to be in your standard units. And this is going to give you 0.34 meters per second as your Vmax, which is going to be your answer for part A. So this is for part A. Find the total energy. So you need to use your energy formula directly. In simple harmonic motion, you have E is equal to 1/2 m omega squared A squared. And after this, we can square the terms and plug in. So here we have 1/2, 0.65, 56.25 times your A. So that's 0.045 squared. And that's going to give you 0.0370 joules. A 80 centimeter long pendulum, as measured from the pivot to the center of mass, is hanging vertically from the ceiling. The string is effectively massless. A student displaces it to the left 9 degrees from the vertical and lets it oscillate. The small angle approximation applies. So that's because our angle is 9 degrees and it's going to be under 15, so we can just assume that it's going to be small enough. So let's start with our force. For this, we have our pendulum and it's hanging from the ceiling. So upwards, we have your Ft. Downwards, you have your mg weight, Fg. So for the pendulum, the restoring force is the tangential component of gravity. I should say tangential. That's your restoring. So now you can use Newton's second law in your tangential direction. Your pendulum will always make this circular path. As you can see, it's like circular motion because that's the radius and the tension force is at the center. It would just spin around like that. And if that was a ceiling, obviously it wouldn't go above that, but if you had like your hand there and you were spinning it, it would be like a vertical circle. So your summation of your forces, MAT, F is equal to MA. And you can plug in your forces. You have negative mg sine theta down and MAT. You can cancel out the masses. You have g sine of theta. Now we can express our tangential acceleration. We have circular motion. So A of t is L squared. And this we can sub back in. And after this, we can divide both sides by L. After this, you have and since this is a small angle, so your equation is just going to be D And we know that with simple harmonic motion, so here we can substitute that in. Now we can calculate our angular frequency, which was what our question was asking us to do. What period should this pendulum have? What would that make its frequency? How are frequency and period related? So omega here is the root of G over L, which we have written there. So in your calculator, we'd plug in 9.8, 0.80, 3.50 rad per second. For period, you have 2 pi over omega. So that's 6.283, 2 pi, divided by 3.50. That's 1.80 seconds. Does the mass of the pendulum's bob affect how long it takes to swing back and forth? Why or why not? We need the frequency. So that's 1 over t. It's this the reciprocal. 1 over 1.80, that's 0.56 hertz. That's the units for frequency. And period is measured in seconds because it's time. So for the mass, in your equation, you have t is equal to 2 pi times the root of Lg, and it does not have mass in the equation to calculate. Therefore, mass does not affect period. Doesn't affect period. Now, okay. What would the amplitude of this swing be? Write a motion equation for its x position versus time graph using the original displacement and assuming it never decays. No friction, drag. So you need to first convert your angle into radians. So our angle was 9 degrees. So you're going to take 9, and it's in degrees right now. Degrees is massless, so pi over 180 degrees. So that would be 0.157 radians. Now, after this, you need to get the linear amplitude. And you can get that by looking at the arc amplitude. You look at the arc. Your arc is equal to L, length of your string, times the angle. So here that's 0.80 times 0.157. That's 0.126 meters. Approximately 0.13 meters if we're looking at sig figs. Draw out the position versus time graph. Put numbers on the axes for the equation showing at least 2 full cycles. Okay, so what you have here is that your pendulum is released from rest. Released from rest. If it's released from rest, at the max displacement left, that means that our initial position is going to be negative. So we know that so you have your equation x of t is equal to negative 0.126 cosine 3.50 t. So for our position time graph values, we have our A is equal to a positive or minus 0.126 meters, and your period is 1.80 seconds. 2 periods is 3.60 seconds. So now we have our table of values that we can use, and we'll just draw the function graph here. So let's label these T1, T5, T7, T8. So your values are going to range from different times and different x's. So again, we can draw this, but with our times. So for our first time, we have a time of 0. For our next time, we have a time of 0.190. Then we have 1.80, 2.70, 3.60 to make this nice and even. So that's our t and that's our 2t. So for your x, it's going to be measured in meters and your t is measured in seconds. So you start off at 0 and then you go to negative 0.126. Negative 126, and you go up to positive 0.126 seconds. Your first value is going to be negative. Then you go to 0. Then you're positive. Then you're 0. And then you're negative again. So that curve would look like this. And we can see this is correct with our graph because it's a negative cosine graph. Cosine x is usually like this. So if you have a negative cosine x, that is going to be a vertical reflection, and it would look like that, which matches with what we have. Now we want the velocity function. So for our last question, we know v of t is equal to dx over dt. We know that velocity, we just plug in. So v of t is equal to 0.126, 3.50 sine 3.50 t. That's 0.44 sine 3.50 t in meters per second because this is velocity. Now let's move on to our next question. When a 75 kilogram person gets into a 1,200 kilogram car, the car springs compress vertically by an additional 0.6 centimeters. So we're asked, what is the spring constant of the system? And ignoring damping, what will the period and the frequency be of the vibration when the car hits a bump? These are reciprocals. So let's write down what we were given. We have the mass of the person, 75 kilograms, mass of the car, 1,200 kilograms, x is equal to 0.6 centimeters. Now converting that to meters, that would be 0.0060 meters, and g is 9.8 meters per second squared. So we need to find the spring constant, and you have to understand what is going to cause this compression. It's caused by the additional weight of the person. Additional weight of the person. So that means that if it's compressed to this amount, we can say that it's in a new state of equilibrium. So that means that it's going to be at a new static equilibrium, which we can say summation of forces 4 is equal to 0. So we can say that spring force of the car is now equal to the new weight of the person, Fw. So now we can write our forces. Fw is equal to Fg, which is equal to mg. So let's set those equal and continue solving. Yeah, so continue doing this over here. Kx, Fs is equal to Kx and our mg. We want the spring constant K, so you're going to divide by x. And you're going to get K is equal to mg over x. So you just substitute in your values, 735 over 0.0060. That's equal to 122,500 newtons per meter. And that's equal to 1.2 times 10 power 5 newtons per meter with 2 sig figs. For your next question, we have ignoring damping. What will the period and frequency of vibration be? Okay, so the car hits a bump. So we're seeing now that the person is in the car. We see that the car and the person, they're gonna oscillate together. So you have to find the mass of this new thing. So your total mass of your system is 1,200 kilograms plus 75 kilograms. That's the car and the person. So 1,275 kilograms. Now we'll use mass spring period. So we have that period is equal to 2 pi m over k. That's just 1,275 over 1.225 times 10 to the power of 5. And that's equal to 0.64 seconds. So for frequency, that's equal to 1 over t. And that's equal to 1 over 0.64, which is 1.56 hertz. Okay. Let's also consider whether gravity will affect this. So I want to ask, if you have gravity and this was on the moon, would your oscillation frequency be different? Well, no. And that's because, like, again, whenever you're asked one of these questions, you just look at the equation, and if it asks, does something affect the thing that you're concerned with? Like, you just see that it's not in the equation. So omega is equal to k over m. There's no g, so it doesn't affect it. A 0.8 kilogram mass is attached to a spring with a spring constant 200 newtons per meter. It is pulled 5 centimeters from the equilibrium and is released from rest. So initially, it's at this spring situation, and then it's pulled 5 centimeters. So that's its natural. And its mass is 0.8 kilograms. Let me just write that. We want omega. So we want period. .398 seconds. We want maximum velocity. So that's amplitude times omega. Our amplitude, 5 centimeters. And then it's 5 centimeters appears to be our max. So we're going to use 5 centimeters here. So that would be its maximum compression and our stretch. So that's our amplitude. That would be 15.8 omega, which we calculated 0.79 meters per second. Now we want our total energy. We're only going to have spring energy here. $200. And that's our solution. Now, next question. A 0.75 pendulum is displaced 8 degrees and is released from rest. Derive the expression for the angular frequency and calculate its value. So, Our length is 0.75 meters. Our angle is 8 degrees. So, like we did before, we have our tangential force. We want this in simple harmonic motion form. We know that this is equal to negative omega squared x, our relationship here. So we'll just have that. And what we need is to divide by L. Or no. Take the root and divide by x. .62 rad per second. When a 70 kilogram person gets into a car, the spring compresses an additional 0.005 meters. Find the spring constant. Well, actually first, I realized I did not finish this question. So that was the answer for A. For B, it's going to equal to 1.73 seconds. Now, you want your linear displacement. Linear displacement is going to be our linear amplitude, because that is the max displacement. So those will be when your graph is going to be at its peaks. We had to first convert our angle into radians because we were given it in degrees. And we use our conversion factor of pi is equal to 180 degrees to cancel out degrees. We get 0.140 rad. Now we have x is equal to L theta. Like we did before, we're going to try to get the sector. And you're going to multiply that by 0.140, and that is going to equal to 0.105 meters. So now we're asked, does mass affect the period? So let's look again at our equation. T is equal to 2 pi root of L over G. There's no mass in this period. So the answer is no. Mass does not affect period, just like we saw before. A 70 kilogram person gets into a car. The spring, when a 70 kilogram person gets into a car, the springs compress an additional 0.005 meters. So mass of the person is 70 kilograms. X is equal to 0.005 meters. We need to get our spring constant. So knowing that F is equal to mg and Kx is equal to Fs, here we know that they're going to be equal to each other. So Fs is equal to Fg, Kx is equal to mg, K is equal to 686 over 0.005, and K is equal to 137200 newtons per meter. Now we need to find the period of the oscillation period when it hits a bump, and the mass is 1,200 kilograms. So for part B, you need to find the total mass like we did earlier. So that's 1,200 plus 70, 1270 kilograms T is 2 pi root of m over k. T is, now we're going to have 2 pi m was 1270 over 137200. Now T is equal to 0.604 seconds. Our last question, does gravity affect the oscillation frequency? Again, like we've seen before in the other question, omega is equal to k over m here. There is no g, so it does not affect, because it's not in the equation.